Okay, so let us look at chapter 7, which is recurrence relations and generating functions. And we are going to start off with 7.1, which is some number sequences. 7.1, some number sequences. Okay, we are going to be mostly caring about sequences of real numbers, which will denote by an. So consider a sequence. Consider a sequence of real numbers which will be denoted an. N is equal to 0 to infinity. And what is this? This is just the shorthand notation for a0, a1, a2, and so on, all the way up to infinity. A1, a2, all the way up to infinity. And related to this sequence is another important sequence, which is the sequence of partial sums of an. Given an is equal to 0 to infinity, we consider its sequence of partial sums which by convention is denoted Sn. N is equal to 0 to infinity, where Sn is equal to a0 plus a1 plus a2 plus all the way up to an. So each Sn is a finite sum of things, and so it's going to be a finite value, right? Now, generally my sequences a1, a0, a1, a2 will be somehow related to one another. You can look at arbitrary sequences, but they aren't as great. You want to be studying some property, right? So what are some of the most commonly used sequences? The most common example is the arithmetic sequence. Example, first, arithmetic sequences. Where each a1 and each ai differs from the previous one by a constant number. So an plus 1 is equal to an plus some amount k, right? And so therefore we get that an plus 1 is equal to a0 plus n plus 1 times k. Okay. And so if I sum up all the a1s from 0 to ai's from 0 to n, therefore Sn is equal to a0 plus a1 plus all the way up to an. Well, there are n plus 1 a0s, right? N plus 1 times a0 plus I'm going to get 1k here, 2 here, 3 here, 4 here, all the way up to n. So I'm basically summing k plus 2k plus 3k plus 4k all the way up to nk, which is k times 1 plus 2 plus 3 plus 4 up to n, which is k times n plus 1 choose 2, right? And so that is the arithmetic sequence and its related partial sums. The other really common sequence that we care about is the geometric sequence. Geometric sequence. Okay, what is the geometric sequence? Well, if arithmetic sequence everything was increasing by a constant number, in geometric sequence everything increases by a constant ratio. So an plus 1 is equal to an multiplied by k. Okay, and so therefore we get that an plus 1 is equal to k to the n plus 1 times a0. Okay, and therefore Sn, which is equal to a naught plus a1 plus all the way up to an, is basically what? A0 plus a0 times k plus dot 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 a0 times k to the n, which is equal to a0 times k to the n plus 1 minus 1 over k minus 1 if k is not equal to 1, or it is equal to a0 times n plus 1 if k is equal to exactly 1. Okay, so these are my two standard sequences that come up very often and have been seen before by you guys, hopefully. And a third interesting sequence that we have seen before at times, but it's not classified as geometric or arithmetic, is the Fibonacci sequence. Example, the Fibonacci sequence. F-I-B-O-N-A-C-C. Fibonacci sequence, which is generally special enough that it is denoted by its own notation and is equal to 0 to infinity. Okay. And what is how is the sequence defined? Well, it satisfies Fn has to be the sum of the previous two terms. So Fn minus 1 plus Fn minus 2. That's its defining condition for n greater than or equal to 2. But this is not the only thing that defines the Fibonacci sequence. The starting conditions are super important because without them you can make the sequence to be anything. So you need to define f of 0 and f of 1. Okay, in that case my Fibonacci sequence looks like n fn 0 1 2 3 4 5 6 7 8 9 10 0 1 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. Hey, 3 plus 5 is 8. Now it got bigger. 5 plus 8 is 13, 21, 34, 55, and it grows on super fast. Right? It's about the same size initially here. If I look at the relative sizes, this is like, oh, you're about the same size. Then suddenly it's twice as big. About thrice as big. 5 times as big. It suddenly grows really fast, right? So this is the Fibonacci sequence. Okay. Let us look at the partial sums of the Fibonacci sequence. And the partial sums we get are n Sn, which I'll just denote by Sn, 0, 1, 2, 3, 4, 5, 6, 7. Let me do it just till 8. And so if you do add these up, you get 0, 0 plus 1, 1, 0 plus 1, 0 plus 1 plus 2, so 2, 0, 1 plus 2 plus 1 plus 1, 2, 2 plus 2, 4, 4 plus 3, 7, 7 plus 5, 12, 12 plus 8, 20, 20 plus 13 is 33, and 33 plus 21 is 54, and you start noticing a pattern, right? There is some correlation here. And so this gets us to think that, hey, maybe these are related to the next sequence. And it is indeed the case when we get lemma for n greater than or equal to 0, f0 plus f1 plus all the way up to fn is equal to f of n plus 2 minus 1. Okay, how are we going to prove this? The proof is going to be by induction. Let us first see if it makes sense. 50 at 8 it is 54, at 10 it was 55, so there it is matching up. 7 7 it was 33, 9 it was 34, 6 it was 20, 8 it was 21. Yes, so that is the correct partial sums that I'm looking at. I am going to prove this by induction. Right? So first, I need to prove the base case. Base case n is equal to 0. Well, if I take n is equal to 0, I just get f of 0 is equal to f of 0 plus 2, which is 2, minus 1. And that is correct, because f of 0 is equal to 0, f of 2 is 1, and therefore both sides get you 0. So base case is done. Now I want to show for n is equal to 1. Induction step. Induction step. N greater than or equal to 1. So assume that it is true for some k. Assume true for n is equal to k. Show for n is equal to k plus 1. Right? I want to do it for k plus 1. So I am going to assume that f of 0 plus f of 1 plus all the way up to f of k plus f of k plus 1. Well, this is equal to f of k plus 2 minus 1, right? Plus f of k plus 1 by my induction hypothesis, because this is exactly equal to this by assumption. Okay. Well, and now the proof is really easy, right? If I have f of k plus 1, f of k and f of k plus 2 and f of k plus 1, this is f of k plus 1 plus f of k plus 2 minus 1, which by definition of the Fibonacci sequence is f of k plus 3 minus 1, which is exactly f of k plus 1 plus 2 minus 1, right? And hence proved by induction. Therefore, f of 0 plus dot 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 plus f of n is equal to f of n plus 2 minus 1 for every n greater than or equal to 0. Okay. I am going to stop this lecture here. We'll try to show more properties about it in another part. I would like to break down lectures in smaller parts so that nothing goes wrong. Let me know if this is fine.